Right, let's get started. Thank you all for coming to the session. This session is technically titled How to Optimize Your Slow Postgres Query Using pganalyze, but even if you do not use pganalyze, this is useful. In fact, a lot of the content I have here is from a previous webinar we did on query tuning, where we had a lot of people attend and find that useful. There's a couple of things I want to talk to you about today. I want to walk you through how we can pick a slow query in that part using pganalyze. What is a good methodology for defining why a query is slow? How can we benchmark queries with explain, analyze buffers, and give a little bit of context on how the planner works. I know some of you in the audience are, even working in Postgres itself, so this is not coming new to you. But what I've found is that oftentimes when people optimize queries, they actually have a hard time making sense of how the planner makes decisions. When we tune queries, really what we have to understand is, the thing we work with, which is the Postgres planner. So I'm going to talk a little bit about planner costing, why this, in my opinion, will never be perfect or can even never be perfect, as in there will always be bad plans, even if, the most amazing planner features are added. Talk a little bit about join order and parameterized index scans and how they cause, good and bad plans, and how we can guide the planner to the right plan. And then I'll end with a few upcoming features in pganalyze around query tuning. Specifically, when you today run explain, analyze manually, we have some things upcoming that essentially will make your life easier using pganalyze. But I'll start by saying, how can we find a slow query? All these screenshots are real screenshots, by the way, but they're definitely, not live right now because that would be too error prone. Just, so, you might ask yourself, why is our database spending so much I/O time or CPU time? And, if you think about queries, really what you end up doing is looking at, which queries have run the database. So in this case, this is a query list in pganalyze, collected from pgstat statements, right? So if you have your own Postgres server, pgstat statement is a D extension to get query statistics, and it can tell you things like how much I/O was spent, how much CPU was spent. What we add in pganalyze is the overtime aspect, right? So we track that essentially not just as a snapshot, but really, what happened in the last 24 hours. Now, what we can also do, and again, this is using standard Postgres components, is we can use the auto-explain extension to get the query plans. What pganalyze does is it extracts these query plans from the logs to attach them to essentially a query object in pganalyze. You can do this yourself, of course, whereas if you didn't explain on this query, you'll get a big text output, which part of the presentation today is about, how do you make sense of that text output? Because that's, I think, oftentimes where, if you have application engineers trying to optimize a query, this is where they'll struggle. Like they might know about explain, but they probably don't know much how to, work with complex queries. Now, what is a good mechanism of how we can debug why queries are slow? One of the things you can ask yourself is a query always slow, or is it just sometimes slow? This is, again, mentioning auto-explain. This is a good way to use the auto-explain section in Postgres because it can log outlier queries for you. So we represent this visually here, but you could think of this ultimately being a text in your logs. And so here we have an example where, on average, this query took 1.4 seconds. That's the PGConf statements data point, but the outlier was 14.6 seconds. Outlier meaning one particular execution that was slow. And if you have a system where, people are interactively making queries, like they're loading a website, this is really the case that's a problem, right? Like essentially, if the outliers are bad, those are the customers that complain because the page doesn't load average, the page loads, on the maximum runtime, worst case. Now, this here is a sneak peek of a still work in progress feature we have for comparing plans. And specifically here, it's just highlighting the difference between those two executions, right? So to be clear, well, this is the average time. I actually picked one that was close to the average time, and that was like a 1.6 seconds execution. And so I just looked at, did the plan differ? In this case, the plan didn't differ. Lots of details to what that means, but we'll get into that a little bit later. But what is interesting here is that we can look at the different plan nodes, right? And we can see like this plan here does an index scan, the function scan, aggregates the data, and has diluted all this function scan. You can see the difference here, first of all, is I/O time is the difference, right? In the good case and the bad case. And then also you can see it's really those two function scans that are the problem as to why the bad case is so much worse. And this is one point I'll start with is you should really understand is the problem you're having in a slow query a problem of the plan shape, right? So are you getting a different plan shape and those are different and slower in some cases? Or is it the same plan shape just with, worse I/O, more rows being loaded, all these kinds of things? And so our goal is that pganalyze gives you that information, but all of this data is available in this plane as well. It's just a bunch of work to analyze it. Now, one thing I'll point out, again, these are real numbers. I was surprised that 25 megabytes of data take 5.8 seconds to load. That just seems absurd, but is a reality when you run in the cloud and you have, lots of concurrency. And so this is something that, is worth keeping in mind as you have things that are non-cache. The typical, customer deployment that we see, which is in the cloud with RDS or on database services, it's just much worse than a local MVE. The other question you might ask yourself, is it the same plan or is it a different plan? So we have a concept called plan fingerprints. Think of that as a MD5, well, it's not MD5, but think of it as a hash function on top of significant parts of the plan. And so the idea behind this is, if you have, here 5 executions like this, trying to understand, are those the same plans or not, is actually not straightforward. Like if you look at the explain text output, it's very much, hard to make that assessment quickly. And so what we end up doing here is essentially looking at the node types, right? So if you have like nested loop versus, merge join, or index scan on this index versus index scan another index, that's really what the plan fingerprint does, essentially, is represents that difference in structure on what is being loaded. Now, my basic debugging loop when I debug a query is, I have a slow query, I realize it's slow, and then I start benchmarking the query. Let's explain and analyze. I then form a thesis on what to change. This is the hard part, right? So it's like, everybody will do this, but, to varying degrees of success, because if you don't understand how the planner works, you will have a hard time forming a thesis of what is happening. And then, you have an idea on what to change, like different index usage, different join order, we rewrite the query, and you will benchmark it again, right? So sounds simple, but all of these can be learned and improved on. In some cases, it's knowledge. In some cases, it's what a product like ours can, help you with. But I think this is a fundamental truth that I believe is correct in terms of workflow. And then at the end, we, found something to optimize, and then we realized it's fast in our testing. Now we have to make the change permanent, which is sometimes non-trivial, right? Like sometimes you might do something like use PG plan to try a better plan, and there is a better plan. You just don't know how to persist that. Today we will not talk about how to persist it, because that's a hard problem. But certainly it is, something to think about, is like, how do we rewrite the queries effectively so that our better plans are actually, permanent. All right, I want to teach you some basics about explain and analyze buffers, just because if you don't know this stuff, you will, struggle with query optimization, I would say. And so that's really that portion there, in that loop. So quick TLDR, if you're not familiar, explain without analyze shows you the plan the planner chose, but it doesn't actually show you the statistics of what happened in the actual run, right? It doesn't actually run the query. Explain analyze gives you the plan chosen runtime statistics. Explain analyze buffers gives you the IO statistics as well. If you want to execute the query, I would say always do explain analyze buffers. There's very few reasons not to do that compared to explain analyze. Unfortunately, it's not the default, but it just gives you so much more data, because where in the plan did things go wrong in terms of IO time. Some simple examples. This is, just regular Postgres. An explain plan looks like this, right? We know it's a gather node, there's a parallel sequential scan, but we don't know how long it took. If we add explain analyze, we know how long the execution was, in this case, 307 milliseconds. And we know how slow or fast each of these plan nodes was. And if we add buffers, we actually get this information about IO timings, if track IO timing is enabled, and the buffers aspect, which tells us how much data was loaded or used. And if you're confused on buffers, that's very common, because it's a weird counter. It's buffer pages, as in one buffer like value is a kilobyte buffer page. Lots of details there, but this is the quick TLDR. Now, we have all this information. We see different plans. Why did the planner choose certain things? There we go. And not other plans. So this is really on the forming a thesis on what you're changing in your queries, right? Because if you don't understand the costing, you'll have a hard time convincing the planner to do something else. And Tom, in a unfortunately not well-recorded talk from PGConf 11 on hacking the query planner, which is a good talk, so talked about how the planner's task is fuzzy, right? There's many different valid plans for the same query, and it's not clear which one is best, right? That's kind of the planner's task is not straightforward. In my own words, right, Postgres planner's responsibilities are find a good query plan, don't spend too much time or memory finding it, and support the extensible aspects of Postgres. All kinds of other things, right? But these are the things that come to mind for me. What the planner doesn't do is it doesn't find all possible query funds. Like there sometimes are plans that are better, but they just weren't looked at in detail for various reasons. It does not change the plan when its expectations don't hold true. This is the most painful part, I would say, of using Postgres in production with many different plans, is Postgres will happily do a bad query all over again, because Postgres also does not keep track of the execution performance, right? There's no feedback loop, at least not today, that will make the planner learn over time. This is where we come in, right? As operators of the database systems, we actually have to give Postgres better information so that Postgres can make better choices. Cost estimation is really what drives the planner's behaviors. Garbage out applies here. If you give the planner bad data, if the planner has bad statistics, it will have bad cost values, right? So it's a very simple math to a certain extent. Now, just briefly talking about cost values, there are different costs you see in your explain output, right? There's the startup cost, which is the effort to get the first row from that particular node. It matters a lot if you have a limit on your kind of explain plan or query. So if you only load the first 10 rows, you're not going to need the whole cost essentially, and the planner knows that. The total cost that's usually what the planner aims to minimize, and that barring any limits. And that's really the part where if you have two different plans, one is worse, one is better, the planner chooses the worst plan is because the total cost of the worst plan was better. Output row count, simple, right? Like we're just returning how much data is being returned from that node, which then influences join behavior, for example, join choice. And the row width is also important, if you have very wide rows, that might impact, sorts, hashes and such. What is cost really? It's kind of this odd unit. It's like currency, I would say, right? Like it's not really a thing, like it doesn't mean much. It's kind of pinned in a sense to the cost of sequential scan, which, you could look at the planner code here, and, essentially it is like taking a value, sequential page cost, which usually is 1, and multiplies it by the size of the table. So the cost of scanning the whole table is how big the table is times 1, right? With the default config. So you could argue that, that's what it's kind of starting with when we're talking about costs. What is the cost of an index scan? Again, if you want to look at the Postgres source, like I sometimes do, you will notice that this is dependent on your index access method, meaning if you have a B tree, that's different than a gen, it's different than a gist, that's different than a PG vector, IVF flat, or HNSW. So this is really specific to the different index access methods. And for B trees, for example, there's a BT cost estimate function. Again, it's open source, you can look at it. And there's a clauseless selectivity function, which oftentimes really impacts how much work the B tree has to do. There's other parts too, I'm simplifying here. If Peter Gagan was in the room, he would tell me that all the B tree code is highlighting the wrong things. But the point is, there are these things in that code that really have a big influence on the cost values ultimately, right? And so we need to understand what input data comes into these like clauseless functions, for example, that then causes the index scan to have a certain cost. But yeah, selectivity is the hard part. Selectivity meaning how many rows are we returning or are we matching really? And so that's, for example, clauseless selectivity in Postgres has to make these decisions. Now it does that by looking at, what are you querying for? Like your where clause, are you saying, x equals 1, y equals 2? And then by default, it will multiply selectivities. So by default, the more clauses you're adding in your where clause, but the more qualifiers, the more specific Postgres will think that things get, which sometimes is not true. And so, see, I have a point about that somewhere here. The usually tunes create statistics to fix those cases. So create statistics is a command. Again, this is one of these tools we have in our tool belt, right, to influence Postgres planner decisions. And if you have this really long where clause, what I can use is I can use create statistics, inform Postgres of what's happening, and then Postgres will pick about that. Another thing, join estimates, we'll skip over that for now. This is not a Postgres planner talk. I'm not necessarily the most experienced person on the topic either. I'm just somebody who's read into these kind of problems a lot. And there's things like increasing table statistics targets and such to improve those. Now, one thing we've done in pganalyze recently was added a new insight for one particular pathological case, which is Postgres misestimating the output rows on a nested loop, which oftentimes, or rather all, the outputs of the one side of the nested loop are essentially underestimated. So in this case, you have this function scan. Function here there's actual row of 1,000 then rows, estimated 1, meaning Postgres thought the function would return 1 row, but actually return 1,000 rows. That oftentimes means that there might have been a better choice in terms of nested loop versus merge join or hash join, but Postgres didn't consider that because of the bad row estimate there. And so this is something we flag nowadays. The action then would be on you, for example, to say, well, how can I influence that? Like functions are particularly tricky, but there's various ways to improve function estimates to kind of see if that improves the plan. And here is a slightly more complex example, which I think essentially shows if you have 2 nested loops, then it's worse. It's really the summary. The other thing I think that is hard to understand at first when you try to do query optimization well is join order and how that influences index usage. Indexes in general is important, but join order has a very big impact on that. And so trying to explain what join order means, suppose we have 2 tables, A and B. We have a sequential scan on table A, an index scan on table B using IDXB, and then we do a nested loop join to join them together. So you could say the join order there is AD in parentheses. That seems logical, right? Now, let's say we're adding a table C. So if index scan on table C, now it reads nested loop join, and then we first join A and B, right? That's the left portion. And then we're adding C into it. So we have parentheses on the first part. We add C, and this is into our join order for this particular plan. This, however, can change. So it could be that this actually is A and C joining first, and then ACB is the join order. Right. This seems very subtle, but oftentimes bad plans will happen when this flips, right? When Postgres decides, for various reasons like selectivity, that the different join order makes more sense. And this substantially, can change index usage, for example. And then how many rows are returned, for example, also. And I'll skip over that. The other thing to note what joins is joining lots of tables becomes expensive to analyze fast. And so if you join more than 12 tables, Postgres will do funky things with the query optimizer. Sometimes works well, sometimes doesn't work well. That's just a hazard to be aware of. And in my experience, there's 3 really important choices that the planner makes that, influence a good versus a bad plan, which is the scan methods, right? So index, scan, and which index, sequential scan, these kind of things. The join order, and the join methods, nested loop versus merge join versus hash join. Now, one thing we've done, and this is currently prototype, is we can detect join order with query plans, right? So, you can do that if you just look at the plan. It just gets tedious because you have to do a lot of parsing by hand. And so you can totally do this, across a set of query plans. So you can say, well, for, this particular query, we're seeing, most of the time the join order of ABC, but actually, that's the ACD. In this case, those actually are table names, as shown there. And this then does, cause a different plan shape as shown on the right. The other thing to know about are when we have parameterized index scans. So parameterized index scan, the reason it's important is because joining, oftentimes you want to, join on things. And an example like this, so we're doing a slant select from T1, which R is ping 2, and we're filtering all T1 field once different, right? So we're saying the data in T1, we can get that by looking for the different field value. Now for T2, the other table, we know the value from the T1, right? So like in the first table, we're essentially getting the Euclid values for doing scan. Now, one could say, for example, if you did a hash join, for example, you could do a sequential scan routine 2, and then, get the data on the other one with an index, and then do a hash join to merge that together. Now, maybe here a quick, primer on how can we restrict or filter what part of the data will be scanned. So, we can have an expression that means certain fixed values reflects no values that are, true or false, have the value of casting in layer, user ID, default, or parameter, or filter based on the table output. That's like we just saw. The simple cases here, right, where everything is in the source query, that can always use an SCN. Third case, where filter on the join condition data from the other table, that's only eligible to use an index scan when it's a parameterized index scan. which means it must be inner side of a nested loop. So by definition, if you have a hash join or a merge join, those cannot use an index, at least for filtering on the join condition on the table. Now, an example of where this shows the material out to parameterize index scan is, you can see here your index scan of the just, and you can see in the index edition, it's not referencing it's now a parameter that shows something the other table. And so that's the loop. So Postgres first have to get this data and then plug that into the other cable to the index scan. Visually shown, the left side kind of shows us, well, it's basically the same data here. But really the important thing to understand is the hash join must be a nested loop in order for that to work. Now, let's switch gears a little bit and talk about, there's more things to learn, right? So I took out a few slides that I think would have made this too long in terms of how Postgres picks query plans. But I think one of the things that, coming back to our debugging loop is, let's say we have a way of forming a thesis. It might be bad join order, it might be bad index usage, maybe missing, maybe you want to try a different version of a query. Now I want to try out the change. Here, one thing that I found really useful for myself, which I didn't know for a long time, was the strategy of debugging things, was I really want to know why a bad plan was chosen, and I can force the good plan and see how the costs differ. So let me see if I can capture this correctly. So we have here, simple example, object ID 123 goes into a planner. Planner gives us a good plan. There's also always a bad plan in a sense. It just has higher cost, right? So the planner, when it makes up its mind about what plan to choose, it will think about, there is a plan that is worse probably, and it's actually not returning because it has a higher cost of 300 in this case. Now, suppose we have object ID 456 goes into the planner gives us the bad plan. Now, why does it do that? Well, it thought about the good plan as well, but the problem is the cost of the good plan was higher, right? So the cost of the plan that we wanted that would have actually had better runtime behavior was 500 in this example, versus the bad plan that had worse runtime behavior had a lower cost of 300. And so this is very important to understand when you're trying to improve query plans. Now, one of the things you can do is you can turn planner features off. So don't do this in production, but do it for debugging, right? So do it for trying to understand why, why Postgres gave you a bad plan or how the good plan would look like. So suppose you get a sequential scan versus an index scan, you can do set enable seq scan off. What this does in everything except, I want to say 18, it actually gives an extremely high cost of a billion cost units to sequential scans, which means that it's extremely unlikely that you would have a sequential scan. And so when you do this, right, Postgres will give you the other plan, in this case, index scans cost 500. Now, what I can do is once I've seen the right plan, right, once I actually get an explain output for the right plan, I can look at the individual parts of the plan and see where did the cost go wrong, right? Like where was the misestimate? So similarly, if I see, for example, I want a nested loop, I could turn off merge join and hash join and see, kind of what is the plan looking like. The other thing, and there's a talk right after this in a different room on PG hint plan. So if you find this stuff interesting, go to the PG hint plan talk. But you can use PG hint plan to force Postgres to do certain plan choices. Don't do this in production necessarily. PG hint plan is kind of not a great extension in terms of how it's written, but it does work really well for debugging. And so you can use it to essentially say, let's see if I have an example here. So here we have a bad plan with a join order of schema column stats and schema tables. I suppose, yeah. So first of all, yeah, right, this is a memorize block. So I can try set enable memorize off to get the better plan. But then I can also, to understand, what was the plan that was not chosen, that had a higher cost, I can give it leading. So this is PG hint plan as an advice. So this is the join order. The hard part about it is you have to use the aliases and it varies. So here we see was the SCS. So you don't ensure to call it SCS and not schema home. In the variables that's the other table, and so we're saying, join these two together in this order. Then also you must use it in it for the other, units, the index standard of index, and the index standard this index, and then also set this remark that. This is an art, right? It's like figuring this out. It's really frustrating. We have some plans in pganalyze to suggest to you what things to try, because we ourselves have like done this many times, even from our own database, and it's just really frustrating to come up with an implementation step. But the idea is once you know this, right, to run the display, and then you know again what was the cost here, right, like on the plan you're trying to go for. So here, for example, the bad plan had a cost of 9, the good plan had a cost of 122. Thus, a bad plan came out. I guess this is a slightly more elaborate example with a slightly different query. But again, it's the cost that matters, right? So like good planning, 1.4 million, bad plan, 970,000, bad plan will be chosen. In this case, memwise was the problem. Bad plan without memwise would have actually had worse cost, wouldn't have been built. A couple of things to know in your tool set when you're trying to guide the planner. If you have simple scan selectivity problems, like on a single table, or you have functional dependency issues, look at create statistics. Functional dependencies are a thing in many databases, and you can create statistics to analyze and prove things. For joint selectivity, statistics targets increasing statistics target will collect more MCVs. That might help get a better joint estimate. Review your cost settings. There's a couple of things I could tell you about that, which in the interest of time, we're not talking about today. The random page cost would be the best example. That's kind of too high on basically any system that hasn't changed it. If you, create multi-column indexes, then think about what the planner really likes, like order by limit is a good example. That, is something where you want to make sure to not give the planner an index that makes it do bad things. Sometimes you might want to materialize parts of a query. So with the with, like CTE statement, Postgres will no longer use this as an optimization fence by default, but you can always use with as materialized. And then Postgres will, do that first and then use that data for something else. So that's a way to rewrite the query to have save the data first. And then one thing I've learned from multi-tenant apps, like, if you have different customers shared in the same system, it makes sense sometimes to add the tenant ID or customer ID into the queries. So you're essentially avoiding, you're reducing your reliance on parameterized index scans, because you essentially can say, I'm always looking for this customer's data. Even if I have 5 different tables being joined, I just, add duplicative where conditions so that Postgres can always use an index scan on the customer's index. And, these things, this is an example before we added some more features in pganalyze, but this essentially, is how when I do analysis like this myself on our own app, I say, here is 2 bad plans. I essentially just, try to illustrate, well, in this case, it shows the bad plan. There's case it shows the good plan. We add a filter condition to always make it good. Also, if you can, please choose better statistics, like inform Postgres on what to do better. Don't use planner hints in production. If you can avoid it, you can, however, with pgconf or Aurora Query File Management is here on Aurora. All right, how are we on time? 20 minutes. All right. So we'll leave some time for Q&A at the end. I do want to show you some things based on all of what we've talked this so far. This is something that, I've done myself, debugging slow queries. I've seen Postgres pathological cases be reported. And so what we've said in pganalyze is how can we make this easier for people so that they can, do better analysis, so that you don't, have to do all this tedious work. There's still some tedious work involved, don't get me wrong, it's just less so. So I'll give you an example here I just ran this earlier, just as a test case. So this is not a screenshot of pganalyze, it's actually a screenshot of our APM tool, Honeycomb. So when we debug slow queries, we're usually interested when does a customer have a bad experience? And so we look at the overall, where is something going bad? Now this here is a list of a particular endpoint and knows that. These are individual traces, right? The multi-telemetry type tracing information here. And I know that, the top one takes 2 seconds. There's a couple of outliers there. Now, what we have in pganalyze is a integration with OpenTelemetry, so we can actually inject tracing spans into your tracing system. And so I can get a link from my Honeycomb trace here back into pganalyze. So that's how I navigated essentially through pganalyze through my APM tool. What I saw when I looked at that plan in pganalyze is I saw, first of all, multiple misestimates of nested loops, which was the new insight I mentioned earlier. I also saw that there was an index and it seemed kind of odd, I wasn't so sure, what was going on there. And then this is where the new things start, which is still in development. Keiko, who's in the back, is one of the engineers working on that. And so if you have questions, feel free to talk to us more about that later at the booth. But we essentially are adding a workflow of pganalyze where like today, all this data we capture is a snapshot of what happened. Right? Like it's a historic snapshot of what happened in the system. With this new experience, what we're doing is we're saying, like when you're debugging, right? So when you're going from like things are slow to, okay, let's go through this loop, let's try to optimize things. We are building an experience around that. This is still in development. We're starting early access soon, so let us know if you're interested to join that. But I want to show you just the idea of how it roughly works. So we start what we call a workbook, which think of it, like a place where you can do your experiments with query optimization. Now, when you do that with a particular query, we take the query and we essentially extract the structure of it. We use the normalized version here. We use the parameters names. It's just a subtle detail. And worth pointing out is one thing that really confuses me is when there's complex query, and just the view of $1, $2, $3, $4, it just becomes complex real quickly. So we automatically give these names based on what they're compared with. You can override that so it kind of makes more sense for you, and you can say the slow cases database ID 1 to 3, the fast cases database ID 4, 5, 6, right? Just makes it easier. Then what we support here is you just paste different query samples for the same query, and we extract the parameters out of it. All right, so again, when you do this manually with pganalyze, you will do a lot of copy and pasting into VS Code or another text editor. And so what we do here is we take, whichever sample queries you recorded, and we find, what values you're looking for, and then we give you the explain commands to run. And this also holds true if you change the query later, right? So this here, obviously, I could just, if I have 3 different like parameters, 3 different samples, you can just add the explain analyze up front. But once I start modifying the query, it gets really difficult. So we generate the explain for you. In a future version of this, we also can do the explain analyze for you, so you don't have to do the work. Here in this case, we just have you copy and paste the output essentially. Now, what we do here is we essentially record a baseline, right? So the mechanism we have here that we say, like there are 3 different parameters we looked at here, time, what was, the without any modification, how these compare. Again, right, there's 3 different planet shapes. We saw different cost, although, and then the runtime here is quite fast. It's actually faster than the earliest screenshot from the tracing tool. The reason is when I do query optimization, I always like to look at the warm cache times. You really got to be careful with IO time, right? So if you compare, what happened in the past, and you run it again, it's gonna maybe be faster, maybe be slower, depending on the cache. And so we recommend always running it 3 times so that you essentially record the fastest possible runtime, which is likely one cache. Now, what we can also do here, we can do a comparison. We can say, well, how do these cuts differ, right? And they are actually different here. Usually this is still work in progress. That the idea is we can tell you, which indexes are being seen, or just sort of plan, like a structural comparison here, or finding A and B are different. And the other thing to point out here is that one in this case had a lot more rows return. Very common case. If like you query different customers' data, for example, one customer has a lot of data, the other customer has very little data. And so this is something that you would see here. And we can also see, and this is just me looking at the actual text plan there, we can also see that the problem here was actually different join order, right? So essentially what was not as obvious here in this visualization right now is essentially that the difference between this red index here and the other green one is because they have different indexes and different join order being used. And so this would be something that I would want to test, right? I would want to test, okay, if I always use a particular join order for all of them, how does that change? And so I don't have the full example here today because I ran out of time preparing it. But the idea is what I would do, right? I would come up with the right PGU plan, but it seems to test. This is something we plan on giving you some ideas on, so we'll give you suggestions on which things to try. But the idea is, at the run the inquiry, force a particular join order, see how it behaves, try, turning off on planner settings. And what pganalyze really does here, and that's, the big value proposition that we have here initially, is just letting you work better than you work today if you do this work. Because if you do this today, you're doing this with, like, if it's a complex query, it's just, again, a lot of like copy and pasting. You're probably not doing it with different parameter sets. You're just doing it, with the one case you saw. And I really think that this will help you work better, help you share that better within the team also. And then in the future, we'll have more, advices and recommendations here as well to suggest you things to try. And I think, let's see if that's all I had. Yes. Oh, actually, here's another screenshot of how this can look like. So again, there's very different plans again. We can help to identify. Like here we're testing, what if we always use this index? And we can understand, it's actually worse if we always use that index. So it's like Postgres actually did a good job, but fix the right index depending on the input data. So not, Postgres sometimes gets things right. Don't get me wrong. But yeah, I think that's pretty much it. If you're interested to try out pganalyze, if you haven't seen a demo at our booth, happy to give you a demo. The new feature sets, again, we're eager for feedback. We're starting early access soon, so let us know if you're interested. And then if you're interested in content that was not about pganalyze, there's actually a longer version of this. We did a webinar on this in June around how the Postgres planner works. I'm happy to send you a link if you ping me afterwards on Twitter, LinkedIn, wherever. And if you haven't seen it, I did a webinar last week on 17, which was less focused on the planner though, it was more focused on overall performance improvements. So that's definitely worth on taking a look at if you're interested.